Sodium-ion batteries as emerging alternatives to lithium-ion batteries, materials, mechanisms, and comparative analysis. Over recent decades, lithium-ion batteries, LIBs, have revolutionized energy storage technologies, enabling portable electronics, electric vehicles, and renewable energy integration. Their high energy density, long cycle life, and reliability have made them the dominant electrochemical storage system. However, increasing global demand has raised concerns regarding lithium resource availability, geographical concentration, and cost escalation. These limitations are particularly critical for large-scale applications such as grid storage and load leveling of intermittent renewable energy sources. In response, sodium-ion batteries, SIBs, have emerged as a promising alternative. Sodium is the fourth most abundant element in the Earth's crust and is widely distributed, making it significantly more cost-effective and sustainable than lithium. Importantly, sodium shares similar electrochemical characteristics with lithium, allowing analogous battery architectures. Consequently, SIBs are being actively investigated as next-generation energy storage systems, particularly for stationary applications. Fundamental operating principles. Sodium-ion batteries operate via rocking chair mechanisms similar to that of lithium-ion systems. During charging, sodium ions are extracted from the cathode and inserted into the anode through an electrolyte medium. During discharge, the process reverses. The system consists of 5 essential components: cathode, anode, electrolyte, separator, and binder. Although the overall working principle is analogous to LIBs, the substitution of lithium-ion with sodium-ion introduces significant physiochemical differences that strongly influence electrochemical performance, materials selection, and cell design. Physiochemical differences between sodium and lithium systems. A fundamental distinction between SIBs and LIBs arises from the intrinsic properties of sodium ions. Sodium ions possess a significantly larger ionic radius, approximately 1.02 A, compared to lithium ions, approximately 0.76 A. This larger size leads to slower diffusion kinetics within host materials and induces greater structural strain during insertion and extraction processes. As a result, electrode materials for SIBs must accommodate larger volume changes and maintain structural integrity under repeated cycling. In addition, sodium is heavier than lithium and has a higher standard electrode potential. These factors contribute to a lower theoretical energy density in SIBs compared to LIBs. Consequently, while LIBs are highly suitable for applications requiring high energy density, such as electric vehicles, SIBs are more appropriate for cost-sensitive, large-scale storage systems. Despite these limitations, the abundance and low cost of sodium, derived from resources such as soda ash and trona, provide a compelling economic advantage. Furthermore, sodium-based systems can utilize aluminum as the anode current collector, unlike lithium systems that require copper, further reducing material costs. Cathode materials for sodium-ion batteries. Cathode materials in SIBs, as in LIBs, are primarily based on reversible intercalation mechanisms, where sodium ions are inserted into and extracted from host structures with minimal structural degradation. Several classes of cathode materials have been developed. Layered transition metal oxides, such as sodium cobalt oxide, are among the most extensively studied. These materials offer relatively high capacities but are prone to structural instability due to repeated Na insertion and extraction, exacerbated by the large ionic size of sodium. Polyanionic compounds, including phosphates, pyrophosphates, and fluorosulfates, provide improved thermal stability and structural robustness. Their strong covalent frameworks help maintain structural integrity during cycling, though their energy density is typically lower than that of layered oxides. Prussian blue analogues represent another promising class due to their open framework structures, which facilitate rapid sodium-ion diffusion and excellent rate performance. Organic cathode materials have also been explored for their sustainability and tunability, although they generally suffer from low conductivity and stability. A notable challenge in SIB cathode development is the hygroscopic nature of sodium-containing compounds. Exposure to moisture can lead to surface degradation, such as the formation of insulating sodium hydroxide layers, which negatively affect electrochemical performance. Therefore, strict moisture control during synthesis and handling is essential. Anode materials for sodium-ion batteries. The development of suitable anode materials remains one of the most significant challenges in SIB technology. Unlike LIBs, where graphite serves as a highly effective anode, graphite does not readily intercalate sodium ions due to unfavorable thermodynamics and kinetic constraints. As a result, alternative materials have been investigated. Hard carbon has emerged as the most promising anode material and is often considered the first-generation anode for SIBs. It provides reasonable capacity, good cycling stability, and relatively low operating potential. Other insertion-type materials include various carbonaceous structures and titanium-based oxides. Conversion-type materials, such as transition metal oxides and sulfides, offer higher capacities but suffer from poor cycling stability due to large volume changes during electrochemical reactions. Alloying-type anodes, involving elements such as tin, antimony, and phosphorus, exhibit very high theoretical capacities. However, they undergo severe volume expansion and contraction during cycling, leading to mechanical degradation and rapid capacity fading. To mitigate these effects, such materials are often combined with conductive carbon matrices. Overall, the large ionic size of sodium leads to sluggish reaction kinetics and significant structural challenges, necessitating further research into stable and high-performance anode materials. Electrolytes in sodium-ion batteries. Electrolytes play a crucial role in enabling ionic transport and stabilizing electrode interfaces. Similar to LIBs, SIB electrolytes must be chemically, electrochemically, and thermally stable, while also exhibiting high ionic conductivity and low toxicity. Organic electrolyte systems based on carbonate solvents, such as propylene carbonate, PC, and ethylene carbonate, EC, are the most commonly used. Sodium salts such as NaPF6 and sodium hypochlorite are typically dissolved in these solvents. These systems offer a wide electrochemical window and good ionic conductivity but suffer from safety concerns related to flammability and unstable solid electrolyte interface, SE, formation. Aqueous electrolytes provide a safer and more cost-effective alternative but are limited by the narrow electrochemical stability window of water. Additional challenges include oxygen removal, suppression of proton co-intercalation, and management of gas evolution during operation. Advanced electrolyte systems, including ionic liquids, polymer electrolytes, and all solid-state electrolytes, are also under investigation. Ionic liquids offer high thermal stability and non-flammability, but are limited by high viscosity and cost. Polymer and solid-state electrolytes provide improved safety and mechanical stability, though their ionic conductivity at room temperature remains a challenge. Electrolyte additives and interfacial stability. Electrolyte additives are essential for improving interfacial stability and enhancing battery performance. In SIBs, fluoroethylene carbonate, FEC, has been identified as a particularly effective additive. It facilitates the formation of a stable and inorganic-rich SE layer, often containing sodium fluoride, which improves coulombic efficiency and cycling stability. However, the effectiveness of additives is highly dependent on the electrolyte composition. In some solvent systems, such as mixtures of EC and PC, stable SE formation may occur without the need for additives. Thus, optimization of electrolyte formulations remains a critical area of research. Separators in sodium-ion batteries. Separators in sodium-ion batteries, SIBs, serve as critical components that physically isolate the cathode and anode while allowing efficient transport of Na+ ions through the electrolyte. Functionally similar to those used in lithium-ion batteries, separators must exhibit high ionic permeability, excellent electronic insulation, chemical and electrochemical stability, and sufficient mechanical strength to withstand cell assembly and cycling stresses. Common separator materials include microporous polyolefin membranes such as polyethylene, P, and polypropylene, PP, as well as advanced ceramic-coated or composite separators designed to enhance thermal stability and wettability with polar electrolytes. However, due to the larger ionic radius of Na+ and differences in electrolyte composition, separator wettability and pore structure optimization are particularly important in SIBs to ensure uniform ion flux and minimize internal resistance. In addition, separator compatibility with sodium-based electrolytes and the formation of stable solid electrolyte interfaces, SE, at electrode surfaces are crucial considerations. Emerging research focuses on functional separators incorporating inorganic fillers, solid electrolytes, or surface modifications to improve safety, suppress dendrite formation, and enhance cycle life. Overall, the development of optimized separators is essential for achieving high-performance, safe, and durable sodium-ion battery systems. Binders and electrode engineering. Binders are essential for maintaining electrode integrity by holding active materials together and ensuring adhesion to current collectors. Poly-vinylidene fluoride, PVDF, has been widely used due to its chemical stability, but it requires toxic organic solvents and is relatively expensive. Environmentally friendly alternatives, such as sodium carboxymethylcellulose, NaCmC, poly, acrylic acid, PAA, and sodium alginate, NaAlG, have gained significant attention. These water-soluble binders not only reduce environmental impact but also improve mechanical properties and accommodate volume changes during cycling. In particular, these binders can enhance the stability of the C layer and reduce electrode degradation, especially in high-capacity alloying-type anodes that undergo substantial volume expansion. Comparative analysis with lithium-ion batteries. While sodium-ion and lithium-ion batteries share similar working principles, their performance characteristics differ significantly due to fundamental material properties. Lithium-ion batteries exhibit higher energy density, faster ion transport, and more mature technology, making them ideal for portable electronics and electric vehicles. In contrast, sodium-ion batteries offer lower cost, greater resource availability, and improved sustainability. The ability to use aluminum as a current collector and the abundance of sodium resources further enhance their economic viability. However, their lower energy density and slower kinetics limit their use in high-performance applications. Therefore, SIBs are more suitable for large-scale stationary energy storage, where cost and longevity are more critical than energy density. Challenges and future perspectives. Despite significant progress, several challenges must be addressed before SIBs can achieve widespread commercialization. These include the development of high-capacity and stable electrode materials, optimization of electrolyte formulations, and improvement of ion transport kinetics. Additionally, most current studies focus on half-cell configurations, and the development of full-cell systems remains limited. Standardization of testing conditions and improvement of manufacturing processes are also necessary to enable reliable performance comparisons and large-scale production. Looking forward, continued advancements in materials science, electrochemistry, and engineering are expected to enhance the performance of SIBs. Lessons learned from the development of LIBs, particularly in electrolyte and interface engineering, will play a crucial role in accelerating SIB technology. Conclusion: sodium-ion batteries represent a promising and sustainable alternative to lithium-ion batteries, particularly for large-scale energy storage applications. Their advantages in terms of cost, resource availability, and environmental impact make them attractive for future energy systems. However, intrinsic limitations related to energy density, ion transport, and material stability must be overcome. With ongoing research and technological innovation, SIBs are expected to complement rather than replace LIBs, occupying a critical niche in the global energy storage landscape.